Hello. Today I'm going to talk about our paper, Minimizing Human Assistance, Augmenting a Single Demonstration for Deep Reinforcement Learning. The use of human demonstrations in reinforcement learning has proven to significantly improve agent performance. However, any requirement for a human to manually teach the model is somewhat antithetical to the goals of reinforcement learning. This paper attempts to minimize human involvement in the learning process while retaining their performance advantages by using a single human example collected through a simple-to-use virtual reality simulation. We aim to achieve this goal by augmenting a single demonstration to generate numerous human-like demonstrations that significantly improve DRL training time on simple tasks and allows the agent to solve a complex task that DDPG plus her cannot solve. The key aspects of our method are a VR-based demonstration trajectory collection system, a trajectory generation algorithm that augments the single demonstration, and a DDPG plus her architecture, which is combined with the generated demonstrations to train the agent. Throughout our work, we trained our architecture in simulations on 3 manipulation tasks: pushing a block, picking and placing a block, and stacking 2 blocks. The first step in our process is to collect the single human demonstration. To make this as intuitive as possible, the demo is collected in a VR environment. In VR, the user completes the goal task once, using a hand controller to operate a virtual version of the robot gripper. The demonstration is then augmented to generate multiple human-like demonstrations. First, random start and goal locations are sampled. Then, the recorded trajectory is scaled such that the start and goal locations of the demonstrations match the generated ones. Finally, the robot uses a noisy proportional controller to follow this new trajectory, and the state action pairs are recorded. Successfully generated trajectories are then used to populate an additional human-like replay buffer, which we initialize with 5,000 trajectories. During training, when the DDPG algorithm would sample from the replay buffer, 25% of the sampled transitions are instead pulled from the human-like buffer, allowing the agent to learn from the human demonstration. Although we found that this replay buffer-based approach worked well on simple tasks, the agent struggled with learning long horizon tasks. One solution we found for this exploration problem was to initialize our training environment using an augmented demonstration trajectory. After the training environment is generated, its parameters are passed to our augmentation algorithm to generate human-like actions. The agent follows these actions for the first few steps before switching over to the DRL controller. This pre-play strategy was only used for our long horizon task, block stacking. We began testing with the simplest environment, the push task, where the agent must move a block along a table to a goal location. When training this agent, we tried providing 2 different types of demonstration, one where the user first picked up the block, carried it to the goal location, then set it down, and the second where the user just pushes the block across the table. Regardless of which demonstration is shown, the agent learns the more optimal policy of pushing the block across the table. However, the more optimal demonstration did lead to a greater increase in training speed. Next, we tested our methodology on the more complicated task of pick and place. For this task, the agent has to learn to pick up the block and carry it to the goal location. Here, we can see a stark difference between the baseline and our method, with a 75% decrease in time till 80% success rate. This pattern of increased complexity leading to a more dramatic improvement over baseline extends to the stack task. In this task, the agent must stack 2 blocks at a specified location on the table. Baseline DDPG plus her was unable to solve this long horizon problem, with a constant 0% success rate. By leveraging a single human demonstration, however, our method allowed the agent to successfully learn the task. On this task, we analyzed the effectiveness of both the human buffer and our pre-play strategy. From our results, we see that either of these strategies allows the agent to learn the task, but combining them leads to the fastest learning. Finally, we completed an ablation study on the pick-and-place task. Here, we tried to identify what parts of our method are key to the agent's success. First, we tried replacing the human demonstration with a demonstration from a previously trained agent. This led to similar results as using a human demo, so it appears that our algorithm can work with any successful demo. Since any successful demo seemed to work, we decided to try auto-generating the expert demonstrations during training. Whenever the agent successfully completed the task, we passed the successful trajectory through our augmentation algorithm and added the results to the expert buffer. However, this approach did not work, resulting in baseline performance, suggesting that an external successful demo created prior to training is necessary. Finally, we tried using a single demonstration without augmentation, populating the human buffer with only the unaugmented human demo. This also led to baseline performance, suggesting that our augmentation algorithm is key to our method. Overall, our results show that a single human example, requiring less than a minute to collect, can be used to significantly improve DDPG plus HER, reducing the pick-and-place training time to under 1/4 of the plain DDPG plus HER approach, and enabling long horizon tasks, such as the stack task, to be solved. We believe that this approach gives an ideal balance of leveraging human knowledge without betraying one of the primary motivations of DRL, to minimize the human effort needed for control. Thank you.